and get started.
Okay. Are you going to start?
Sure.
Or should I start?
Well, I'll do the intro and I'll hand it off to you for the second slide.
Okay.
So tonight we'll be talking about our first classification algorithm. It's called Logistic Regression. That name might be a little confusing since we've discussed in the past that classification and regression are two different things. But we'll actually get into that a little bit and maybe discuss why it was given that name. But before that, Shreyas is going to talk for a couple minutes about the final project for this class.
All right, okay. Hello, everyone. Hope you guys are all doing well. I would like to talk about the final assignment, as Jeff said. So we want each of you guys to come up with an idea of a project. And the project should use any concepts learned during the AI camp and should aim to help the community or the environment. You don't have to actually build a project, but come up with an idea and how you'll build it. We encourage you to actually build this project at a later time, but actually building a project is not part of the assignment. We would like you guys to create a 2-minute video explaining what your project does, how it helps the community or the environment, and how you're planning on actually implementing the project. And this is very good practice, as you would often have to pitch your project idea and plan to individuals before actually starting your project. And your project idea might also have an opportunity to get featured on our community AI website. And further, the top 10 ideas will get recognition in the form of medals. So as you listen to these lectures, we recommend you to think about how you can use what you learn in these lectures in your actual project. And we'll post all of this information on Google Classroom for your reference. So with that being said, I'll pass it on to Jeff, who'll get started on today's lecture on logistic regression. So Jeff, do you want to get started?
Yep, thank you very much. All right, so we're going to try something a little bit new here, and we're going to spend a minute discussing tonight's learning objectives. So as I noted in the Google Classroom today, we've had some students who have pointed out that a lot of the topics we're discussing are actually pretty advanced, and we recognize that. So what we want to make sure is that people in the class, we want you to understand that you don't necessarily need to know every single detail that we present. We're really trying to focus on the big ideas right now. So tonight, we'd like to really focus on reviewing basic classification terminology and concepts. We're going to learn about this concept of separability and how that might impact the accuracy of a classification algorithm. And we're going to learn the basics of linear regression. So I'm going to give some details about how it's implemented, but really we want you to focus on what the algorithm's doing and more or less how it works. And then we'll observe an implementation of logistic regression on a data set that's fairly similar to one that we studied on Tuesday night. So let's dig in. You recall from our first lecture that classification is one of the two main subsets of supervised learning. So there's classification and regression. So on, I guess, last Thursday, we talked about our first regression algorithm. That was linear regression. Today, we're going to talk about our first classification algorithm. That's logistic regression. So classification problems require the prediction of a class or a label associated with each observation in the data set. So we gave a few examples of those in lecture 1. So given a picture of an animal, we might ask the computer to determine its species. So here the classes would be dog, cat, horse, or dolphin, etc. Whatever classes comprise our whole set of pictures. And as a second example, we might want to determine whether or not a client will default on a loan based on their financial history. So there's two classes here, whether the client defaulted or repaid the loan on time. And as a third example, we might determine whether credit card charges are fraudulent. So the two classes here would be fraudulent charges and legal charges. And we'll actually break down these problems a little bit further. We may have discussed this very briefly, but there are couple different types of classification. So one is binary classification, and that's when there are two labels or classes associated with the data. So as a first example, whether or not you repaid the loan or defaulted on the loan. There's only two options, so those are the two classes we're trying to predict. As a second example, in the fraud example, transactions are either legal or fraudulent. There's only two options. However, the third example we talked about, there were three or more labels or classes associated with the data. So the image is assigned a label from the set: dog, cat, horse, dolphin, etc. Since it's a little bit easier, we'll begin by focusing on the binary classification problem, but the transition to multi-class classification actually isn't too difficult. So as a first example, let's take a data set that's kind of similar to the one we talked about last week. And this is, again, a fictional data set which I created in order to demonstrate the concepts. It's a binary classification problem. And there are two inputs, a student's homework score and the number of hours they studied for a test. And then we measure whether they passed the test or failed the test. And as you can see, in general, as students scored better on the homework, they have a higher probability of passing. And as they studied more, there was a higher probability of passing. But it isn't perfect, right? We've got that one we might call outlier, where the student scored 80 on the homework and studied for 8 hours. It's surrounded by points in which the student passed, but it happened that that student failed. So again, there's not a perfect relationship here, but there's a general trend that's persistent. So since that trend isn't perfect, this is an example that is not perfectly linearly separable. So let's talk about that a little bit. Here are two examples that really do a good job of explaining the concept of linear separability. Oh, I got my labels mixed up. That's not good. On the left is an example where it actually is perfectly linearly separable. So I'm going to have to make a note to myself that I made a mistake here. On the left, it is perfectly linearly separable because as we draw a line through the data points, all the students who passed fell on one side, and all the students that failed fell on the other. On the other hand, the data set on the right is not perfectly linearly separable. Shreyas, can you see the drawing I'm doing on the screen?
Yep, I can see the drawing, yeah.
All right, great. So on the right, the data set is not perfectly linearly separable because no matter where we draw the line, there will always be at least one example from the other class on the wrong side of the line. So if a data set is perfectly linearly separable, it's possible that we could achieve 100% accuracy. That means we could classify all the points correctly. But if we see the example on the right where it's not perfectly linearly separable, we can't get 100% accuracy, at least not with an algorithm like logistic regression. It might be possible to use a different algorithm to get 100% accuracy, or we might need to collect more data in addition to homework scores and hours studied in order to understand whether students passed or not. All right. So let's again discuss the goals of classification. So we wish to create a model which predicts whether an individual will pass an upcoming test based on their homework score and the number of hours studied. As we mentioned before, in this case, our model cannot be 100% accurate. So instead of assigning labels, let's actually predict a probability that each student will pass. And there's a note on this screen that says that accuracy is generally measured by the number of correct predictions divided by the total number of observed predictions, or observations predicted, excuse me. So if we had 100 students and we predicted 95% of their outcomes correctly, we'd have an accuracy of 95%. But there are also other measures of model performance which can be studied independently. So you're free to look these up, but we won't be talking about them tonight. We might have an opportunity to talk about them in a later lecture. But we might be interested in the true positive rate or the false positive rate or other measures called precision, recall, and the F1 score. So it's not important that you remember those terms, but it's important to know that there's multiple ways that we can measure how well a model's doing. All right. So let's begin by talking about logistic regression. And as I've noted on the top of the screen here, some of the concepts might be a little advanced, and it's not necessary that you follow every bit of the derivation that we're about to go through, but let's just focus on what the model's trying to do. It's really trying to assign a probability to a class or a label. So logistic regression is a classification model, despite its very confusing name. And that's because with logistic regression, while we're trying to predict a class, what we're actually doing in a sense is performing regression on the probability. So we want, based on the inputs, to predict the probability that certain observation is in each class. So let's let P denote the probability that a student passes the test. And for our historical observations, we already know whether the student passed or failed. So we'll assign P equals 1 if the student passed, and P equals 0 if the student failed. And then we can define the odds that a student passes the test. And this is just defined as P divided by 1 minus P. Again, these details aren't super important for your understanding of the algorithm, but it's good for us to take a look at why this works. And next, we'll define the logit function, which is simply the natural logarithm of the odds. So again, we denote the probability as P, we define the odds as P divided by 1 minus P, and then we define the logit as the log of P over 1 minus P. Here, when I write log, it actually refers to the natural logarithm. In your math classes, you might have referred to the natural logarithm using ln. However, in a lot of machine learning applications, you'll see it written as log. So I wanted to keep the notation similar to most machine learning textbooks. And finally, we'll estimate the logit of the probability using a linear function of the inputs. So this almost looks exactly like linear regression, which might be kind of helping explain why logistic regression got its name. So we'll define the log of P over 1 minus P equals theta 0 plus theta 1 x1 plus theta 2 x2, where x1 is the homework score and x2 is the number of hours studied. And theta 0, theta 1, and theta 2 are again our parameters. And now let's solve for P. So since that right-hand side of the equation is pretty messy, let's just call it Z for right now. So we're going to set Z equal to theta 0 plus theta 1 x1 plus theta 2 x2. And we'll do a little bit of algebra. So we'll set the log of P over 1 minus P equal to Z. We'll take the inverse of the log function, which is raising each side from the power as a power of E. And then we'll solve for P. So we'll multiply both sides by 1 minus P. We'll distribute the e to the z through that term. We'll collect all the terms with P on the left side of the equation. We'll factor the P out and divide both sides by 1 plus e over z. So we get this P equals e to the z over 1 plus e to the z. And actually, we generally write this a slightly different way. If we multiply both the top and the bottom by e to the negative z, we get this function here in the red box. And it's called the logistic sigmoid function. And more commonly, it's just referred to as the sigmoid function. So I've plotted the sigmoid function here on the left, and you can see what it looks like when the input to the sigmoid function is a big negative number. The sigmoid is very close to 0. And when it's very close, or when it's a very large positive number, it's very close to 1. And you can see why this might be a nice function to use when computing probabilities, because if you recall from your probability or statistics class, the probability of an event happening always needs to be between 0 and 1. It could be 0 or 1 as well. So whenever z, we'll go to the next slide actually, before I dive too deep into that. So the line on the right side of this screen, which does a fairly good job of separating the passes and the fails, can be described by the equation z equals 0. So again, we set 0 equal to theta 0 plus theta 1 x1 plus theta 2 x2, and we can plot that line. And the goal, of course, is to find the line so that all observations that fall on one side of the line belong to the same class. But as we discussed earlier, this example is not linearly separable, so we can't do that. But that's okay. So what we see here is that when z is greater than 0, and that's everything above and to the right of the line, we observe that the probability p that a point belongs to the positive class is greater than 0.5. And when z is less than 0, the probability that the point belongs to the positive class is less than 0.5. And it turns out that as we get further and further away from the line, above and to the right of it, the probability gets closer and closer to 1 that the student belongs to the positive class. And as it gets further and further to the bottom left of the image, we get more and more certain that it does not belong to the positive class and actually belongs to the negative class. All right, so I'm going to draw here real quick. So in this area up here, we're very, very confident that those two students are going to pass the test. They fall pretty far to the right and above this line. Down here, I'm struggling a little bit with my drawing tonight. That's okay. The points down here, we'll use the spotlight. Those we're very, very confident that the student is not going to pass. And then here in the middle, we have a little bit less confidence. Those probabilities are probably closer to 0.5 that the student passed the test. So how do we actually implement this? Well, first we'll transform our class variable into a numerical value. So in the original data set I showed you, we just had class labels. So a student may have gotten a 90 on the homework, and they studied for 10 hours, and they passed the class. Well, our algorithm needs numerical outputs, so we'll call passes 1 and set fails equal to 0. So we discussed that briefly a few slides back. And next we need to define our cost function. So again, we've talked about this a few times already, but the cost function essentially tells us how well the model fits our data. And we recall that the probability is given by this function that we just discussed. P equals 1 divided by 1 plus e to the negative z. And we're going to represent this function with the Greek letter phi. Some people say phi, phi, either one is probably fine. And this again is called the sigmoid function. Logistic regression uses this special cost function defined below as follows. So j of theta, so remember this is the cost function, which is evaluated at our current approximation to the parameters, is the sum over all points, negative yi times the log of phi of zi, minus 1 minus y times the log of 1 minus phi of zi. So again, remember that phi of zi is computed first by computing z sub I, which is given by this equation here. The right-hand side of the equation, z equals theta 0 plus theta 1 x1 plus theta 2 x2. So you might be asking, why do we need such a complicated cost function? If we remember the cost function from linear regression, it was really quite simple. We were just computing the mean squared error. So we'd compute our prediction and then subtract off the actual value, square it, sum those up, and divide by the total number of samples. Well, this cost function is actually almost as simple and elegant, but we need to really kind of break it down and look at the cost for a single observation I. So let's drop the sum and pretend we're looking at a single observation I. And so I've just rewritten everything that's inside the brackets. So let's look at that equation and say, what do we get if y sub I equals 1? So if the student passed the test. Then the equation simplifies greatly. So if y sub I equals 1, we get 1 minus 1 here. So this multiplier out in front of the log on the right side becomes 0. So the second term here disappears completely. Y sub I is 1, so we'll just drop the y sub I term here, basically. We'll just imagine a 1 out front, and we get the equation to be negative log of phi of z sub I. On the other hand, imagine y sub I equals 0, so the student failed. Well, in that case, the first term disappears because we'd have 0 times the log of phi of z sub I. And again, we'd have 1 minus 0, so that coefficient of the log term just becomes 1. So we end up with a negative log of 1 minus phi of z sub I. All right, so for our observations, this equation simplifies greatly. And now let's look at those two terms. So let's look at the negative log of phi of z sub I and the negative log of 1 minus phi of z sub I. So when the y equals 1, the cost function looks like this blue curve here. So when the predicted probability is close to 1, the cost function is very close to 0. So essentially, we get penalized if we make a very accurate, highly confident prediction, but the cost function gets very, very large if we predict that the student would fail, especially if we predict that with very high confidence. On the other hand, it's the exact opposite when y equals 0. When y equals 0, if we predict that the student fails, we get a very low penalty in the cost function. But if we predict that the student passes, we get a very, very high penalty. And if we predict something in the middle, basically if we're not sure if a student passes or fails, we basically just get a moderate penalty. Not too big, definitely not as big as we see at the extremes. So essentially what this tells us is the logistic regression model, if it has the ability, it wants to predict things with as much confidence as possible, but it doesn't want to be very confident and wrong. So being confident and right is okay, but being confident and wrong is not okay. So here I've summed that up a little bit more concisely in English terms. The model gets a very large penalty if it is confident but wrong. The model gets a very small penalty if it is confident and correct. And the model gets a moderate penalty if it shows low confidence, regardless of whether it is right or wrong. So how do we find the optimal parameters? Well, we talked about that on Tuesday. we'll apply gradient descent or something similar. And we take that and try to find the minimum of the cost function. Just as always, we're looking for those parameters which minimize the cost function. So you might be wondering, okay, well, how does that work with multi-class logistic regression? So if we have more than two classes, obviously we can't just draw a line down the middle and say that one class falls on one side of the line. So what we actually generally do is we adopt this concept called one versus rest, or OVR. And essentially, for each of the classes, we'll train an independent model. So here, we see that these light blue points belong to one class, the yellow points belong to another class, and the brown points belong to a third class. So what we've really done here is trained 3 models. And for each model, we score every point in our data set. And whichever one has the highest probability that that point belongs to the data set, we'll essentially give it that label. So we define a first model and say, does the point belong to the blue data set, or does it belong to the rest of the data set? So that's the yellow and brown. Then we define a second model where the target variable is essentially the class that the yellow points belong to. So it's yellow versus the rest, blue and brown. And third, we define a model for points belonging to the brown class, and it would be brown versus yellow and blue. You can read a little bit more about this from in scikit-learn's documentation, and that's actually where I got this image from. This actually belongs to a very common example, one of the first tests you generally apply for multi-class classification. This is called the iris dataset, and there are 4 measures of certain aspects of the flower called the iris. So the sepal width and sepal length, as well as the, I believe, the petal width and petal length as well. And using that information, those 4 measurements, you can generally classify with pretty high accuracy which subspecies of iris the flower belongs to. So now we're going to go to a code demonstration. Tonight's demonstration will use Python, since last time we did Octave. And we'll be using 4 packages: pandas, that will be used for the data manipulation. sklearn has a built-in logistic regression model. Seaborn, that's used for creating some nicer plots. And matplotlib, which is used for some basic plotting. So I'm going to exit out of my slides and open up Python. Shreyas, can you verify that you can see my code?
Yeah.
Okay. Yes,
right now I can't see your code.
Nope. Uh-oh.
Oh, yeah.
All right.
Yeah, I can see it now.
All right. So I'm going to try to make this a little bit bigger. Okay. So somebody a couple classes ago had asked about different IDEs, that's integrated development environments, that people use for coding. This is one that I happen to like. It's called Spider. It's maybe not as fancy as something like PyCharm, but it's pretty good, and I like the simplicity of it. And if you've come from a background where you know MATLAB or Octave, it actually behaves pretty similarly to the MATLAB or Octave GUI. So first, just as before, we're going to load the pandas module. We're going to load that as PD. So just in case you aren't familiar with Python, when we say as, that basically just gives us the ability to rename a module with a shorthand variable. So instead of having to type pandas every time we want to use a pandas function, we can just type PD. We'll do the same with the pyplot module from matplotlib. We'll import Seaborn, and then we'll import Logistic Regression from sklearn's linear model module. So some of this probably looks sort of familiar. Shreyas demonstrated this last week, but we can use pandas to read a CSV. So I've created that homework scores and hours studied data set, and we will load that, and we'll take a look at the first 5 rows. That's what this data.head command provides. All right, so I've loaded the data set. This should look familiar. The first student got a 99 on the homework. They studied for 6 hours and they passed the test. Second student got a 95 on the homework, studied for 0 hours and passed the test. The third student got a 71 on the homework and studied for 0 hours and failed the test, and so on. All right. So now that we have a good understanding of what the data looks like, we can start doing some manipulation. First thing we'll do is let's count the number of observations. So we can just ask for the length of the data frame. We'll store that as n, and we'll define our explanatory variables and our dependent variables. So our explanatory variables are the homework score and the time studied in hours, and the dependent variable is the outcome, whether or not they pass the test. So we'll reassign these variables to x and y, since that's kind of a traditional way to name things. So we'll say x is equal to the explanatory variables of the data frame, and y is equal to the dependent variable within the data frame. And since we, as we pointed out in the lecture, the algorithm wants a numerical value for y. It doesn't want the text descriptions of pass and fail. We're going to use this slick little line of code here to turn y into a numerical column. Essentially, we just ask the question, is y equal to pass? In Python, the value true, the Boolean true, can be interpreted as the number 1. So if we just multiply 1 times the vector of trues and falses, it actually returns a vectors of 0s and 1s. Pretty convenient. If you aren't familiar with that, don't worry about it, but it's just a trick you can learn later on. And so let's look at the transformed target column now. So down here, we've transformed the output from passes and fails to 1s and 0s. So if we can get both of them on the same screen, we see the top 5 rows were pass, pass, fail, which is the same as 1, 1, 0, 1, 0. All right, great. Looks like we've done a good job. So you can probably ignore this line of code where we reshape y. That's just to make some later plotting work out nicely. It's turning y from a 2-dimensional matrix into a 1-dimensional vector. And now we can visualize the data. So on the x-axis, we'll plot the homework score. On the y-axis, we'll plot time studied, and we'll color the points differently depending on whether or not they passed or failed. And then this S just determines the size of the points. And we're going to label each of our axes. All right. It wants to let me me try that one more time. Apologies. It doesn't like when I rerun that line of code since I've already reassigned the variable y. Right. Shreyas, can you see this plot?
Yep, I can see the plot.
All right, great. Sorry again about the technical difficulties here. It wants to keep switching windows when I run the code. So this plot should look very familiar. This is almost exactly the same as the plot we showed during the lecture, where all the points for students that passed are on the top right side of the image, and almost all the students that failed are on the bottom left side of the image. All right, so we'll close that and go back to the code. Now that we've kind of taken a look at our data, now's a good time to actually start doing the predictions. First, we've got to train our model. So we start by instantiating the logistic regression model. We'll just call that LR. And this solver is a parameter that you may have to set depending on what version of sklearn you've downloaded. But LBFGS is very similar to the gradient descent method. It's really just a fancier version of trying to find the place at which the gradient equals 0. So next thing we do is we fit our model. Again, that fitting the model is the same thing as finding the optimal parameters. And then we can ask the fit model, what is the intercept and what are the coefficients? So we can go ahead and actually just take a look at those real quick. This should happen very, very fast. It does. So the intercept is negative 15.85. That's the same as the theta 0 we showed in the slides. And the coefficient should be about 0.2 and 0.4. So those correspond with theta 1 and theta 2, respectively. So here's our theta 0 is the intercept, theta 1 is 0.198, and theta 2 is 0.394. Okay, and then let's plot the decision boundary. That's what we can call that line that separates the two classes. So I'm doing a little bit of data manipulation here just to understand the range at which I should be plotting. So like the minimum X value and the minimum Y value. I will calculate some points on that line based on the equation that Z equals theta 0 plus theta 1 X1 plus theta 2 X2. And then I will plot that line and shade everything below the line gray so that we can see where the points lie. And then I've, again, set the X and Y limits so that we're focused entirely on the set of points. Uh-oh, all my points disappeared. I'm going to have to rerun a set of code. All right, here we go. So now you can see the decision boundary that logistic regression came up with. It's this line that separates the two classes fairly well, but you see that there are 3 failures above the line and 3 passes below the line. So it actually didn't do super well, but I think it's the best we can do with one single straight line. All right. And now, since the model can predict whether or not a student passed or failed, we can apply this model to the original data points and see what it predicted for each of those students. So we can use the predict function from the the logistic regression algorithm. and we'll figure out which ones of our predictions are correct. And we can calculate the accuracy by essentially figuring out how many of the values were correct divided by the total number of values. So we'll go ahead and do that. And it tells me that the model made correct predictions 82% of the time. So not great, but not bad because it's a very simple model, essentially about as simple as we can get in terms of classification models. And we can also go ahead and plot which ones we got wrong. So you can probably ignore this code, but it's makes it a little more clear on the image. So now I've put a box around all of the points which were wrong and also put an X through it. So we can highlight that 3 of the points, 3 of the students that passed were predicted to have failed, and 3 of the students who failed were predicted to have passed. All right. And if you recall from the beginning of the lecture, what I told you we were doing is we're actually predicting probabilities that students passed. So we can take those probabilities and assign each student to a class, but we could also just look at the probabilities on their own. So what I'm going to do here is I'm going to compute the probabilities, and I'm going to create a scatter plot again of each one of the students. On the x-axis, we'll look at their homework score again. On the y-axis, we'll look at the time that they studied. And then we're going to color the data based on the probability that they passed. And here, if we take a look, we can see that there's a gradient from the lower left to the top right. These points in the top right are yellow, which means they're very close to 1, which means there's very, very high confidence that they passed. On the other hand, down here near the lower left, all of the points are purple, which corresponds to a probability of passing very close to 0. And those points in between, we have a little bit less certainty, so they were given this bluish green color. And most of the ones that we got wrong didn't have, the model didn't have too much confidence. They were all in this region very close to the line. So with that, we'll wrap up the demo. I will make sure to post this code to our Google Classroom. But with that, we can open it up to any questions. Feel free to unmute and ask, or type the questions into the chat, or ask in our Google Classroom.
Dr. Willard?
Yes.
So around when we started the lecture, I was still a bit confused as to why we used odds instead of probability by itself. Could you explain that?
Sure. So this is maybe a little bit more advanced that we want to get into for the whole class. But let me pull up this slide. It turns out that if we were to predict the probability directly, instead of this log of the odds, this variable z that we've defined on this slide here would actually be potentially unbounded. However, as we kind of noted, probabilities, in order to be a true probability, need to be between 0 and 1. So when we predict the log of this p over 1 minus p, we get that nice behavior. There are probably other ways we could have defined it, but it turns out that this sigmoid function is actually very convenient and ends up getting used in a lot of different places within machine learning, including neural networks, which we'll talk about next week. So terms of a more definitive reason why we use the odds instead of the probability, I don't really want to get into that tonight. We can maybe talk about that more in Google Classroom. But really, the main reason is so that we get this nice curve here that's bounded between 0 and 1.
Okay.
So I see a question here about time studied being displayed on the y-axis of the graph. You're correct. It is not the independent variable. It is common in math that we plot the the dependent variable on the y-axis. But when we have multiple dimensions, we can't exactly do that. So here the dependent variable, whether they passed or failed, was actually being plotted in a third dimension, and that was based on the color of the point. So I also see a question, what happens if there are points on the line? Realistically, that probably will never happen. I'm sure we could design a model so that it does, but in the real world, it rarely ever does. And what you generally do is just assign those points to the positive class. It doesn't really matter because you've got a 50% probability either way. So it might impact your accuracy, but it won't impact the cost function at all. So essentially that would just mean that the model is completely split on whether it thinks it belongs to the positive or negative class. I see a question from Max about the problem on the third homework. There have been several questions about that. So we'll post something to Google Classroom, but let's keep the questions focused on the content of the fourth lecture. So I see an earlier question, is it still perfectly linearly separable if the point is on the line? I would say the answer is no. But again, that kind of relates to the previous question. It really just depends on what decision you make, whether you assign the point to the positive or negative class. But again, it almost will never happen in practice. Do we have any more questions tonight? See, we have a couple questions about the final project. Shreyas, do you want to answer that? Or I guess...
I believe Shraman answered it.
Yep.
Right.
So again, the point of the final project is really to bring to the forefront a lot of ideas on how we can improve the community and the environment using machine learning and AI. So if you've done a project before, I'd say that that's fine. It's probably still a great thing for people in the class to learn about, different ideas for implementing ML projects for the good of the community.
Dr. Willard?
Yes.
For homework assignments, like from now on, since we're diving into more complicated topics, will we have to know how to code certain parts?
No, so we are not requiring any coding to participate in this class. So the homework will be based on the large concepts in the lectures, and not specifically on implementation details or how it's used in the code. But I would recommend that you take the code from the class demos and play around with it. Maybe even try to find a different data set online and see if you could use the same technology to do a similar analysis on the different data set. Now, again, that's just an extension if you feel comfortable with it. If you don't, just getting the concepts that we discussed during the lecture is probably a good start.
Okay, I understand.
All right, are there any other questions this evening? Okay, well, with that, we'll wrap up the lecture for tonight. I believe Shreyas will post the lecture later. I will post the class slides, and I will post the code demonstration all to Google Classroom. And there will be a little delay in the homework being posted, but we'll try to get that up this evening as well. Have a good night.
Thank you, Jeff. Bye.
Thank you, Jeff.